Hello everybody, this is Dan Rodriguez here, and let's talk about reliability. So this is a different channel now, stats only, nothing else. Today we're going to talk about the Kappa statistic. There's many different measures of reliability, but what we're looking at here is what's known as inter-rater reliability. So we want to look at how two people rate something and whether or not they agree or they don't agree. In this case, we're rating something as either positive or negative. Like for instance, we may be rating whether a student should matriculate to our university or not, or should somebody win a contest or not win a contest? Should somebody be awarded something or not awarded something? In medicine, it might be whether someone should be diagnosed with hypertension or not having hypertension. So inter-rater reliability occurs when two different individuals are rating somebody. There's also measures for more than two people, but that's beyond what I'm doing today. Intra-rater reliability is contrast to inter-rater reliability. Intra-rater reliability would be when the same individual is rating somebody twice. So for instance, if somebody was taking blood pressure to determine whether or not somebody should be diagnosed with hypertension, it would be taking that blood pressure reading twice. So make sure you understand the differences between those. So the equation we will use here is known as the Kappa statistic, and it is the proportion observed agreement minus the proportion expected agreement divided by 1 minus the proportion expected. So how much above and beyond what is expected can be attributed to our measure, the difference between the observed and the expected measure. So let's take a look at this, of what exactly all these terms mean. So P sub 0 or O would be the percent observed agreement, and P sub E would be the percent expected agreement. We'll use, in this first table, I'm just showing you how we end up calculating expected agreement. Observed agreement is easy. I just count how many individuals agreed, either in the positive sense or negative sense, and divided by the total. So that's not much of a complicated calculation. For the expected agreement, we'll lean on what we know about probabilities, and we'll rely on the multiplication and the addition rules of probability to arrive at this expected agreement. So let's say we'll allow Q to represent person 1. So this is one of the two people making the observation. Let M represent person 2. So if we look at this cross-tabulation table, person 1 can either rate the observed individual as positive or negative. Person 2 can rate the observed individual as positive or negative. We'll let 1 represent positive in this sense. Positive represents positive, and negative represents negative. The sign's positive, plus sign represents positive, and negative sign represents negative. So if we look at person 1 can either say that the observed individual is positive for whatever. Let's just use disease. Say it says hypertension. So rater 1 will say the observed individual has hypertension, right? Because they rated it positive. So we're looking at the marginal values here. These are called margins, right? If rater 1 says the individual does not have hypertension, right? We'd have this Q here, Q0. If rater 2 says the observed individual has hypertension, right? They're given this value of M sub 1. So yes, I was right. 1 is positive and 0 is negative. And then if rater 2 says the individual does not have hypertension, they would have this value M0. So what we see inside these 4 cells here is the confluence of the different observations. So if rater 1 believes that the observed individual has hypertension and rater 2 believes they have hypertension, it would intersect right here. So we have a Q1 and an M1. So that means that person 1 believes the individual has hypertension and person 2 believes the individual has hypertension. Notice that I say and here. And is important because and in probability implies multiplication, right? So this is an and scenario. In this cell to the right here, we see that person 1 believed that the individual did not have hypertension, and person 2 also believed that the individual did not have hypertension. So we have the Q0 and the M0. Again, this is another AND scenario, so we have Q0, M0. So what you see in these cells is, like I said, the intersection of the two observations. When I say we use probability theory, because there's two ways that we can have an agreement. Either both person 1 and person 2 rate the patient as positive, right? Positive for hypertension in our example, or both person 1 and person 2 rate the observed individual as negative for hypertension, right? Get this Q0, M0. So these are two situations. So for both of them to have to rate the individual as positive, that's a product of the probability of each. So what's the probability that person 1 rates the individual as positive? That's whatever the cell value is, called Q1. So this is going to be the sum of whatever the values are in these two cells, right? It's Q1 divided by N divided by the total. So that's a proportion, right? And then individual 2 or person 2 has to also rate the individual as positive. So in M1 cases, person 2 rated the individual as positive, so we'd have M1 divided by N. And then this is a bunch of different individuals, not just one individual, right? So what we have here, M1 represents the number of times person 2 found somebody positive, and M0 represents the number of times person 2 found an individual negative, right? And the same going across here, person 1 found Q1 positives and Q0 negatives out of the N. So in order for us to have agreement, you have to have agreement here, right? Or in probability terms implies addition, right? Or the addition rule of probability, or they'd have to agree here. We're using the addition rule minus we're ignoring the place where there's a joint probability, because you can only be in either any of these four cells are mutually exclusive. You can't be in two simultaneously, right? These two simultaneously. Can't be in these two at all simultaneously. You're either this one or that one. That's it, right? So we don't have to subtract the joint probability. Okay, so that's how we would calculate the expected proportion expected agreement. So let's go to some heuristics here. So we'll calculate kappa using this equation up here, right? After we get the expected and the observed agreement, and then we'll get our kappa value, and we'll use these heuristics to interpret. Values below 0.4 represent poor agreement. Again, these are heuristics. Heuristic means that rules that people follow. Whatever. That happens a lot in stats. People have these rules, and they say this is the cutoff. Values between 0.4 and 0.75 represent intermediate to good agreement, and values above 0.75 represent excellent agreement. Let's do an example here. So I'm a big fan of Invader Zim. I don't know if any of you are. So I was thinking of my two lab techs, Zim and Gur, working for Dr. Rodriguez. They're assessing the inter-observer reliability of the new R test for disease D. Disease D is a very difficult disease, yes. So we're hoping this R test will work very well. They each screen test results from the same 200 participants. Zim identified 75 positives. So we look at Zim. There were 75 individuals positive according to Zim for disease D. Gur identified 60 positives. Right? They agreed on 40 positives and 105 negatives. So let's calculate the kappa and interpret the results. So let's split the screen up here. Yes. So we can have our results side by side. I'll shrink this bad boy a little bit to make it fit the screen. There you go. All right, so here's our kappa equation. The proportion observed minus the proportion expected divided by 1 minus the proportion expected. What's our proportion observed agreement? We had 40 cases in which both Zim and Gur believed the individual is positive or agreed that the individual is positive for disease D. We had 105 where they rated the individual negative for disease D, so that's 145 out of those 200. So that's our observed agreement, proportion observed, 0.725. Pretty easy, right? Our expected agreement, well, they can occur in two situations, either Zim and Gur, so I say and I use the intersection symbol here. If you know things about sets, that's an intersection symbol. So either they both agreed on the positive, or means addition, or they both agreed on an individual being negative for disease D. So let's see, Zim rated 75 out of the 200 as positive, so that's why we have 75 divided by 200. Gur rated 60 out of 200 as positive. Yes, and Gur was probably eating pizza. I don't know if you ever watched Invader Zim. He loves pizza. He loves biscuits, pizza, cows, and a whole bunch of stuff. Tacos, yeah, loves tacos. So positive situation. Or they rated them in the negative situation. For Zim, it was 125 out of 200. And for Gur, it was 140 out of 200. So we do the product of these two because of the multiplication rule. And means multiplication. We're going to add because of the or. And then we're going to multiply again because of the multiplication rule and the and here again. And we got a kappa value of we get a expected proportion expected agreement of 0.55. All right, so now we subtract the proportion expected agreement from the proportion observed agreement, just like I noted in the equation here. We divide it by 1 minus the proportion expected agreement. You see my handwriting is so beautiful. I don't know how you could live without me. 0.175 divided by 0.45, we get 0.389, or roughly 0.39. Based on our heuristics, that represents poor agreement. So, well, just almost getting close to okay agreement, but it's pretty much poor agreement. So that, my friends, is how we do the kappa statistic. It's actually not very hard. If you want to do these kind of equations, well, just understand the probability rules and you'll always be okay. All right, thank you.